I'm sorry, I can't hear the audio.
And okay, so okay, now you can hear. Good. So the good old fashioned turn it off and on again. All right, so we had this curve and we want to find a 60 kilowatt spot. And we're going to use bisection method, second method, and Newton's method. And well, okay, if you cannot calculate numerical derivatives, then you can calculate the Newton's method regularly. And you can use, okay, that's one thing. You can use Microsoft Excel, but programming this should be relatively easy, but it's still doable with a calculator. Regular public calculator has a bit nasty time typing in all of those variables, but it should be doable with a programmable calculator really easy. So that one, we're going to have a little look on estimations and also just connection between estimating functions and finding roots as well. And then we had this announcement that Mark was going to hold this week's. So this one is something I cannot make it, but Mark will be there. So we'll have a look at these exercises. I'll still try to make the demos. And let's see if this is changed already, because I'm sure many of you have been enthusiastically waiting the ability to have lectures straight from 8 till noon on mathematics on next period's Wednesdays, but it's changed. This one will be exercises. So we will have a lecture in the morning, and then we will have exercises. The annoying part is that we're going to have our demo lecture in the evening, and we're going to have the other lecture also in the evening. So I'm still not really happy about the schedule, but it's better than it was. So the second period schedule is slightly changed. Probably we're going to have relatively short demos here, but we'll need the 4 hours of lecture time. And then we'll see how it goes. So hopefully we can pack relatively much on the Wednesday mornings, and maybe can stop a bit earlier on Mondays and Thursdays. Yeah, do ask.
Will it still be 8:30 on Wednesday?
Can
I go back to 8:15?
Yeah, we'll probably go back to 8:15 because we'll need some time also to. It's still not on the same room. We'll need to go from here to 2305, which is mildly annoying. Okay, but then on to this week's topic. So we'll start with linearization. So it is a lot about approximating functions, something you already had on the linear case, so which we had some uses. So if we're having a real, and also related to this is how many times that you need to evaluate the function itself, which is something that is being asked on this week's exercises. Because if you're having a really complex function, then if you can reduce it into a more simple function, your calculations will end up being a lot faster with the expense of some accuracy. So the linearization was this formula. So essentially we're picking what's the current point, which is the FA, and then multiply the difference by f dash a. So essentially this says that that y equals approximately x plus delta x times the slope k. So x minus a is here the delta x, and then the derivative stands for the slope at point A. And yeah, if you remove the x from what I draw on the board, so we have only delta x times the slope. This is delta y. Comes up in an example in a short while. So graphically it was this. We have some function that we don't want to calculate necessarily. This is a really simple function. And then we instead draw a straight line and notice that the value Lx, the linearization function, is usually pretty in the vicinity, pretty close to the real function value. And if we're close enough, we can calculate, roughly estimate how much error we have. Then we're saving a lot of computing time. Also, this week's exercise, we're talking about Newton's method. If you solve that for where the linearization goes to 0, so the root of linearization, which is relatively trivial to do, you have just invented the Newton-Raphson method. So solving where the straight line it's the x-axis or whatever the horizontal axis is called. And yeah, we didn't actually invent it. It is known for a relatively long time. Actually, similar methods were already known before TAT. And also, some of you have introduced to the Stetson-Harrison method. So usually, mathematical methods are commonly discovered or improved upon by several people. So you end up having names for methods which have more than one name on those. So we're having a few examples how this works. We're having 3 functions. I'm going to show you the 2 first ones, and then I'm going to ask you to do the third one. The third one, you can use the difference method there. So assuming how much is the change, and then by that we can assume that the change is roughly relative to the formula here. Okay, so let's do this step by step. I always try to show your work. So we're going to linearize this square root of 1 plus x near x equals 0. And then the linearization was function value at 0, which is 1, plus the slope at 0, in this case, well, and then the difference. So the slope, where we are going to now need the chain rule, which is down there for you. So f dash is half times 1 over square root. Put the inner function in it, 1 plus a is over there, times the derivative of a, which is just 1. So we get just half, because the square root of 1 plus 0 is square root of 1, which is 1. So there it goes. X minus a when a is 0 is x. So our linearization function is 1 plus half x. So let's compare. The red line is the straight line version, and then the curve is the actual function. So when we're having values close to 0, seems to hold. Of course, the linearization has values where the actual function does not, so below -1. So good to note the domain. And then as we go to higher and higher values of x, then this is going to have more and more error. Let's try another one. So the linearization formula, same thing again. Fx is 1 over x, a is half, so f at the value of a is 2. Then the derivative, 1 over a squared, a is half, so it's 1/4, minus 1 over a squared, so we get -4. X minus a is x minus half, so we're going to get 2 minus 4 times x minus half, or 2 minus 4x minus 2, which is just minus 4x. Now we're going to see a little problem, because this point happened to be where the curvature of this original function was the highest, so it's going to relatively fast have a relatively high error. If we had picked any other point and that lap of this slope, we would have estimated a lot better. And of course, this function we were estimating, 1 over x, does have a discontinuity at 0, so the error blows up over there. Okay, snowballs. So it is a ball which has a radius change from 5 to 4.92, and how much, what is the size after the radius changes? So when we had this Lx equals FA, I should remember this from memory, but I do not. And plus F dash A X minus A. Did I get it right? I'm gonna go back to enough to, yeah, that was the right way. This is a nasty part to do a sign error. So this is the same as the original. So if we look at this, so this would be the B5 plus that one is delta B. And delta V we estimate, so what we get is V5 plus that's essentially V over R delta R. So this formula popped up probably in your so relative change formula popped up in the material we had previously for estimation. Probably no, it's not right. You had this 4.3 pi R squared delta R. In which somewhere there is a delta R over R because we're missing one R from volume. Otherwise, units wouldn't. Delta R was 0.08. And we have here 25 times 3, so this is 125. 0.08. That's 8 times 125 is 1,000, so this is roughly 10. So we get, well, pi over 3 is roughly 1, so we get 40. Yeah, and this was, of course, they have a minus here, so we get minus 40. Something funny. I'm probably having a decimal error somewhere. Let's see. And then the volume at 5 pi. Well, the volume of a ball over 3 pi r cubed. Well, over 25 times 25 is 125 times 25. Well, times 100 because we're having here 4. So we're having. So for n, I'm probably making some kind of errors, but we're getting something like 12460. Did anyone get anything like that? And yes, you usually cannot cancel out pi and 3. It is having some extra errors here, but going roughly kind of by hand waving the numbers. I'm probably having an error somewhere, so radar calculate for yourselves. Times, yeah, that goes 1,000 divided by 100 is 10. Yeah, but we're roughly on the ballpark of the change being roughly minus 40.
Should be 24.73.
Okay, then there's a large error somewhere.
That's the exact change.
Yeah.
If I just input that,
Yeah.
that should give like 24.33.
Okay.
Which is about 1.6%.
Okay.
I guess
Yeah.
No, 1.6.
Yeah. And that change here was of roughly 10,000. Yeah. So that's just small even. But yeah, I'm having an error somewhere. But that's the general way you could use this test. Now, of course, the ball example, just like the previous quantity and price example is usually such a simple calculation that you would not need to use these methods, because you could calculate well just by themselves. So. Okay, so how to calculate the error for this? So then we need the second derivative. So now we need to go to higher derivatives again. So I'm gonna skip the proof for this, because usually if I would need to use this error calculation, I would just check the handbook at what it was, because I can't remember it. So the second derivative of capital X here over 2 times the difference in value to the power of 2. And here this capital X is some number between x and a. So if the function does not behave nice and has large differences in the second derivative, then the potential error is larger. And based on this, we do, so the second derivative may change in the estimation interval. So we do have 3 corollaries related to that. And first derivative is change in function value. Second derivative describes what the curvature of the function is, how much it curves. Because now when we're having estimations that assume that what if the function was just a straight line, then the curvature is going to affect how accurate our estimation is. So if the second derivative does not change sign on the interval, then the error has the same sign. And if we have some number that limits how high the absolute value of the error is, then we can use that value instead to estimate the error. So then the absolute value of the error must be below this maximum rate of change. And the third one is slightly longer. If we can find not only some k, which stays always higher than the curvature, but we can also find essentially 2 numbers which limit at how high or how low the curvature will be. Then we can use these numbers to estimate how much it roughly curves, and plus and minus those can be added to the linearization estimates, and the true value of the function will be between those estimates. So the lower value for curvature correction, the higher value for curvature correction, and the true value must be between those two. If those are still the same sign, so the true the function curves always in the same direction, then we can improve our approximation that the function value is the linearization plus n over 4 times the change. So we can add a second term there to improve this one. And these are really nice because, as we noted, we had earlier on the examples, we had slightly, well, this is especially slightly more difficult function, but it became 1 plus half x, which is really simple to calculate. So with the really complex functions, if we can get the error down and have some kind of a nice formula like this for the error and get results, then if you need them really fast, we'll talk on real-time systems. So in milliseconds or fractions of a millisecond for some control purpose, for example, then this is really a step forward for using microcontrollers probably, so Arduino board or something like that. So this E is error function, and those bars mean absolute value. So now here we get a much smaller error here. So now here's an example how to calculate the error interval. So the error does also have a sign, which means that how much on is the other end where our true value might be. So we're going to estimate F26 based on putting a tangent line on the square root function at 25. So again, just doing stuff on the linearization formula, we get that the estimate is 5 plus x minus 25 over 10. The error estimate is slightly more complex. We get this x to the power of minus 3 over 2. And our estimate, well, that's really simple. There's 26 minus 25 is 1. So we have 5 plus 1 over 10, which is 5.1. And now, because that's slightly complex to calculate, this 8 times x to the minus 3 over 2. Well, based on the power, we know that it goes down to higher x. So we're just going to use it with 25. So 25 to the power of 3 over 2 is 125. And that's higher than what the actual value would be. So we're going to put that, and it comes a nice round number. So now error must be smaller than minus 1,000 parts. And thus we know that the true value of the function must be within the interval of that has the upper bound of 5.1 and the lower bound of 5.099, which is 1,000 parts less. Actually, if we use the correct value for the error function, it will be even slightly smaller, but close enough for engineers typically when we get to under 1,000 parts. What was the actual value of square root 26? Anyone to calculate already?
So 5.09.
Okay, so yeah, we're actually relatively close to the 099 part. So yeah, what if we added just the error term because it was close? And okay, what if we calculate the error for this thing and add another error term to get better? So this is called Taylor's polynomial. Essentially, adding error correction over error correction, and we can figure out that it has this kind of a formula that's shown on the slide here. That's a basic principle. And for example, if we want to calculate E, close to x equals 0. Well, okay, e is a nice example here because the derivatives of e to the x end up being, well, e to the x. So the derivative here doesn't change, and when we calculate derivative values at a, which our estimation point is 0, well, e to the power of 0 is 1, so that all of those derivative point estimations go to 1, and downstairs into the fractional of n, and then we can start calculating the estimate, which as we get further and further down the line is 1 plus x plus half x squared plus 1 over 4x cubed, and so on and so on. So the first estimate would be 1, not very good. Even worse estimate than our earlier suggestion that e might be 3. Then let's add the correction term to it, so that was the 0th degree. So what if it was constant? So the second degree estimate is 2. Okay, still not very good. Second degree estimate is 2.5, already getting a bit harder. And the third degree estimate already 2.666 and continuous, and so on. 6 and 7 both give us roughly 2.718, which is relatively close to actual value. If 3 decimal is enough, then we could replace that with a 3 decimal approximation, or a 6 degree approximation. This is occasionally useful if you have a function that you can approximate, but it's really hard to differentiate or integrate. Then maybe you can replace that function with a Taylor polynomial, which is, well, a polynomial, and polynomials are quite easy to differentiate. So that way you could then get rid of a lot of work, assuming you're close enough for the accuracy. Error term ends up being this. So essentially the previous one, and I expand it, so it's a n plus first derivative of x divided by the fractional of n plus 1 times the change to the power of n plus 1. And again, this capital X is some value in this estimation interval. And this does have a sign, so when you add the error term to your estimation, you get an interval where the true value must be. Okay, let's do another estimation to this square root of x. So we had the previous result, so let's use it. And the error term was that, so we get a second degree estimate of 5.099. Error term here is positive to 10,000 parts, so now we got that the upper bound must be 5.0992. It was what, 02? But these essentially should swap signs, so then we get closer and closer each successive iteration.
Yeah, it was 02.
Yeah.
So that it goes. Actually, it's 01951 and not 02.
Yeah. Okay.
It's not that different.
Yeah.
Almost 02.
Yeah. So good reminder. It's not always closer to the error corrected term, but as we add successively more terms, then we can narrow down the gap. Common estimates, okay, EX we already had. This sigma, so this funny thingy there, which has n equals 0 and infinity on it's below and above, that's a capital Greek letter sigma. So that stands for sum of those terms from 0 to infinity, or if we don't want to calculate infinite amount of numbers, then as many as we need until we have a sufficient amount of decimals. So usually when you calculate decimal approximations and you want a certain number of decimals, then when that amount of decimals no longer changes, then you probably can be sure that you've reached the required accuracy. Sine has also an approximation of there's kind of a series. So we call this Sarja series. And cosine similarly has a series. Logarithms do have an estimation series. And 1 over 1 minus x does have a series approximation of x to the power of n, and so on. These are some of the more common ones. And I can't remember what I did last time. Probably the examples were on the board, which takes a bit more time than just reading the PowerPoint, because this was the intended material. But let's have a look at. I'll need to find the file from my own computer now. I'm going to drop it to the course as well. So if you want to follow on your computer, then you can. But this thing is not as carefully edited as the previous one. It still has last year's stuff. So yeah, oh yeah, it's indeterminate forms. So these indeterminate forms now refer to the L'Hopital method of finding limits and thereby differentiating. So Monsieur L'Hopital was French, so they don't pronounce the H. It's not Mr. Hospital. No, okay. So we had an example of this. What's the limit of sine x over x? That was 1, even when it goes to 0 over 0. And we did that by showing you that, well, sine x stands for the height of a triangle, and x, if we're using radians, is now the angle of the sector, and we could use that and the triangle and sector volume to show that this approach 1. But there are other methods of finding this out. 0 over 0 is not defined, so we cannot just substitute. Also, other things that are not defined is infinity over infinity. That's not defined. 0 times infinity is not defined. Well, infinity minus infinity is also, it's not 0. It's undefined. 0 to the power of 0, yeah, no. So, okay, 1 times infinity is probably 1. And 0 times, yeah, 0 times 0 is actually probably 0. I'll need to check. Those are essentially decided by convention. So we can use some, but first, introduction to the big O notation. So this tells what it, if we talk about computational complexity, you're going to run there in the big O notation as well. So there it talks about upper bound of how many computing operations are going to be done within for some length of input typically. And in mathematics, we're now talking about the upper bound of the error term. So can we find some function u which shows what's the upper bound of the value for the function? And if we have some, and now upper bounds are kind of Big O notation tells that what kind of a degree is the error following. So if we find just any function that multiplied by some constant k always has the chain error, the value is smaller than this function, then we can tell that this is the true function value is lower than our estimating function. So this forms some kind of upper bound, and how tight this upper bound is, and that's a bit. So if it's the smallest possible upper bound, then that's usually a bit harder to prove. So if we add a function as some estimate plus an error, then the difference between these functions is going to be the error. So if we start estimating things, we can find this kind of if our gx is the estimating function, then we can tell that the error progression follows our so-called big O function. For example, how to do it for our Taylor polynomials is that the big O does follow this x minus a to the power of n plus 1. So we skip the constant, which was the derivative of n plus 1 degree. This is how we read the big O notation. I'm not completely sure why this was in. You probably missed it last year from what we just did for Taylor polynomials, and that's why it was on the following lecture. Anyway, indeterminate form. So we want to find these. One way is if we get close enough with our Taylor series, is that we replace with sufficient accuracy with a Taylor series or maybe a Maclaurin series. I probably need to talk more about Maclaurin series. We haven't talked about those last year. We should. These are necessary, at least in electronics. So one way is that if we just replaced, for example, the sign, which is its approximation, which does not go to 0, until we could get a real limit out of that. Another way is using L'Hopital's rules, but these are usable, so not for all indeterminate forms. L'Hopital's rules can be used only for 0/0 or infinity cases. So if our functions that form the parts of, in the case of sine over x, our function f is sine x and our function g is x, then we both have, when they're approaching the value where we want to take limit, they are approaching 0, then L'Hopital's rules say that the limit of the quotient of these functions is the same as the limit of the quotients of the derivatives. So now we replace the denominator x with 1. Okay, so the denominator disappears, and we replace the numerator sine x with cosine x. So what we get is our estimate is or the limit should be the same as cosine x at that point, and cosine 0 is 1. So our limit of sine x over x is 1. Second rule, now if these go to plus or minus infinity, then similarly, Similarly, if we get this infinity of infinity, this is also the limit of function divided by function. This quotient is the quotient of the numerators and denominators derivatives. The same thing. So with these, we can estimate a lot more limits than previously, and with relative ease. Okay. Now, not all of you had done integration before, so let's have a look at what integrals could be. So we had a short introduction on the analytical side that an integral was an antiderivative. But where we actually define the integral is that we're calculating the area of a function. So the sigma notation, in this case, we had already a taste of this. So we had sigma on series, and sigma notation is that we calculate the values of function at certain points. So how we read this as sum of f from fi, where I goes from m to n, is usually these m and n are integers with m smaller than n. So, and f must be defined at all of these points. So we calculate the sum, and this is a shorthand way of writing this sum of different function values. We have some rules for those. So if you reduce these things to their basic elementary school forms of value of f at 1 plus value of f at 2 and so on, you can clearly see that we can take the common factors out. We can divide by pluses. So we can have the first rule shown here, which is actually combining two rules. So you can take the common factor out, and then you can also change the sum to be, so if you have two sum of two things, yes, then it can be divided two. So which way you calculate them. And then we can also do variable changes. So if we have this sum from m to m plus n, that's the same thing as if we shifted this, that we sum from 0 to n, this I plus m. This is also relatively useful for integration. And we could easily figure out summation rules for what's the sums of 1. Well, okay, here that's relatively easy. If we need to sum 1 how many times, then we could get the multiple out. And if we sum 1 n times, then the answer is n. Summation rules for I. So now I'm going to for a moment stop sharing my screen. So we're trying to figure out if there's a rule for taking a sum of I from, so doing this from I equals m to n. First thing is we start just, let's say 5 to, well, let's say 0 to 5. So we get 0 plus 1 plus 2 plus 3 plus 4 plus 5, which is 6 plus 6, yeah, 15. If we just started from a smaller number and went towards higher numbers, so okay, sum from 0 to 0 is 0, 0 to 1 is 1, 0 to 2 is 3, and so on, we probably could then figure out that actually we can take the average of this and have a multiple of how long the interval is. So this is, so the sum, if we look for this, so 0, 1, 2, 3 would be 6. So if this is the to n, so we could probably start seeing a common factor emerge here. So summation rule for t is I equals 0 to n would be 10 I is n times n over 2. So average value times the number of or the length of the interval. Also would go geometrically. So if we consider this as an area, then what's the area there as it expands and just goes from the actual wouldn't be this, it's increasing. So what we get here is a height times base divided by 2, and when height and base happen to be the same, we get the same formula. We can find similar rules for I to the power of 2. So first by tabling the values a little bit, and then figure out if we can see that, and so on. And a similar way we could probably develop rules for integrals as well by reducing the area. One way to calculate areas is take sums of the sub-areas, which is the way we are traditionally going towards the definition of the integral. So we had this earlier that the Riemann sum would be the average height of the interval times the length of the interval. And that's the definition of the Riemann sum. And if necessary, if we cannot estimate the average height of the interval, we could then, or the average value of the interval in general, then we could estimate that maybe more accurately in smaller intervals. And because we have the same rules here, well, okay, when we're having the same value, then the sum here is 0. If you consider these are the definite integrals. So if we use the area explanation, how large is the area from A to A? Well, the width is 0. So whatever the value of the function at that point, then the definite integral here is 0. From A to B, if we need to swap those around, maybe it's easier somehow calculate those. So we can have the negative, that one, A, and then A to B, same as with the sums. If we have two functions inside, we can divide at the plus to have two integrals, and we can take common multipliers out, just with like sums. Integration by parts, if it's easier to integrate, so that we integrate to an intermediate point and then divide there at that point, we can also do that. I should have examples of these, but especially if we consider things like some kind of a wave function, then let's say we have functions over here is defined as piecewise, so kind of a semicircles. then it might be easier to reduce this to its graphical interpretation, that here if we have some radius r and here we have some radius r, then we could calculate these by areas. Of course, because these are if these are the same r's and this would be actual half circles, then we know that the integral would be 0 because these cancel out each other. So also those tricks help occasionally if you can divide a larger interval into parts where you can see that some parts cancel out each other, probably not that much to calculate. And then there's a triangle inequality. It's a bit difficult to read like this, but what this says is that because of this reason that if it dips below 0, then we are supposed to reduce these parts from sum. So if we take the absolute value of the function and integrate that, the result is always greater than the absolute value of the integral. Essentially, the integrals, how much stuff there's inside the integral, is always less than the sum of the absolute value of the parts. For odd functions, well, like that one actually there, integral from a to a, if we had the 0 point, if we had the origin here, we can see that this would be an odd function. So, am I, by the way, sharing the screen? Yes, I am. So I was drawing, it's probably not gonna show on the video, so I was drawing this, which is 2 semicircles or half circles. And if the origin is there where in the middle, then we can clearly see it's an odd function, and we already knew that that's gonna cancel out. And for even functions, then which are symmetric by the vertical axis, then we know that we could also divide at 0, which is useful if the function value at 0 happens to be easy to calculate, and then multiply 0 to a by 2, and we can easily calculate the value of the integral. Mean value theorem, we had this on the very early parts, and it has an interpretation here as well. So if we can find the mean value of the function, then for integrals we can then just multiply the interval by the function's mean value at that interval. So this f with a line on top of it is not the vector f, it's the mean value of f. And if we put it other way, so if we want to calculate the mean value of a function that's continuous, so we cannot just take the point values of a function and calculate the mean value based on that. If we know the integral, then we can take the divide the integral by the length of the interval, and we get the mean value of the function. So this comes immediately from here. So when our we have assumed, so the mean value theorem was that a to b fx dx is the same as the interval length b minus a times some fc, where fc is this mean of fx at that interval. And now if we simply divide both sides by b minus a, then we see that this f equals 1 over b minus a, integral from a to b fx dx. For example, what would be the average impulse as some interval, and then we could calculate easily what's the acceleration as a physical example. And well, that was it for the basics of integration. Any questions at this point? First exercises, I think, tomorrow, and then Markku, as I mentioned earlier, will be holding the exercises on Thursday. Should be relatively easy on this. If you have just a pocket calculator, then there will be quite a bit of inputting the numbers, but other than that, shouldn't be too hard. So on exercises, the questions are, it actually has already answers that show your work that you calculated the answers with intermediate results as well. So it asks what's our RPM value, how many iterations did you need to do, so how many times did you need to repeat the calculation, and how many times did you need to evaluate the function. Now, there's two ways to do this. In some cases, we might want to calculate the function again, but if you just do a table of the, am I screen sharing? I should be screen sharing. Okay, so otherwise it will be for our people on the internet. So what the questions were, what are the RPM value, how many iterations do we need to, and how many times that you need to evaluate the function. So let's have some whatever function as an example of application of this method. So we're having a function like this, and we want to find the root using the, well, let's use the bisection method, and our x1 is here. We need to evaluate fx1. Our x2 is here. We need to evaluate fx2. That's two function evaluations for the first iteration. And then x1 minus x2 over 2 is here. We need to evaluate again here fx3. We check if it's within required accuracy. Well, it won't be with this method yet, but it was negative. We replace that one, go here, so x4, fourth evaluation for the second one. But now if you're smart, you remember what the value of here is, so you don't need to evaluate the function again. There was positive, replace positive side halfway, and so on. And what's the accuracy of this method on the horizontal direction is that when the interval, now we know that because this was negative, we know that it must be this. When the interval is when the interval length is smaller than 2 times the error, you know that the center of the interval is within the error of the true value. Is this clear why? So now, what if the true value is, in this case, it's here? Then the error over, if error here would be this distance. And on the previous interval, it's still, we don't know where it is within this area. The error is still quite large, but if we even without knowing what's the value of the function at this point, then we know that it already must be within here or within here. So that's 2 times the same direction, or same distance, different directions. So that way, if we just by the interval length between the endpoints, we can estimate where the true value must be in the case of the bisection method. And the same thing if we use the second method. But there, when we do not have, okay, in the second method we do have kind of a endpoints, but it's working, and as well as the Newton's method, it's working on change. So in case of Newton's method, if we need to estimate the accuracy, if we start here, draw the tangent, it hits here, draw here, draw the tangent here, and so on. Then we need to estimate how much this value changes. So the first step, we have a huge jump, probably high amount of error, but then we should get closer and closer with each step. So this jump is already smaller, and this jump is really small over here. So when the last jump, so when xi minus xi minus 1 t is smaller than the error, then we're probably inside the required accuracy. So this notation means that with this iteration and with previous iteration, so the difference in value. This should help you through also the exercises. Just in case numerics, do put all the intermediate results there. There are probably ready-made programs that you can just say that just do this for me, but you are expected to return something else as homework than a single command. That's not sure that you know what's happening inside that command. All right, if there's nothing else, if there's questions, do ask. If there isn't.
So it's sufficient enough to just return the intermediate results instead of the actual calculations. If we do
well, yes, do, okay. This is an important part that when you're having this kind of a show that if you just want to do the intermediate results, then first show your method, how you got those. So in pen and paper, we would then put iteration formula, which you actually can find from the slides, and then show the intermediate results. That's enough proof of your work that you've done it. If you do it with pen and paper, then maybe also show how you calculate that. But for example, in an Excel sheet, it's probably good enough that you just show the sheets. And if you have a program, then return the program code. I'm not sure how you do it with that if the program is in your calculator at all, but maybe type it in Notepad or Word or something. These should not be terribly long programs. My versions of the second method program has one line for the function and one line for the second method. All right. That's it for today, and see you tomorrow.
It's 8:30 or
8:30 tomorrow still, yes.